Hello and welcome back to Abstract Linear Algebra, the video course where we talk about some more topics in linear algebra. And in today's part 43, we continue our discussion about the Jordan normal form. In particular, we will look at an explicit example for the Jordan chains and the Jordan boxes. However, as always, before we start with that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the link in the description, you can download a lot of additional material for the videos. For example, you find quizzes, exercises, and my book about linear algebra. Now, before we go into our explicit example, let's first look at the abstract picture we have for the Jordan normal form. This means we look at a complex vector space V and a linear map L that goes from V to V. And now the general idea is that we fix a basis B in V such that the matrix representation with respect to this basis is a Jordan normal form. Hence, what we can put into this picture is Cn and the basis isomorphism phi b. So as always, our matrix representation can be seen as a composition of linear maps. And now what I want to show you is that the Jordan chains from the last video actually give us the Jordan boxes for the matrix representation. Hence, what we have to do is to choose the basis B with suitable generalized eigenvectors. And in order to make our life easier, let's assume that the corresponding eigenvalue is given by 0. Moreover, the names for the generalized eigenvectors are given as in the last video, which means x with two indices. The first index tells us the number of the chain, and the second number is our level for the generalized eigenvector. So if we have 3 levels for the first chain, we go with 1, 2 and then 3. And now for the second chain, let's say we only have 2 levels. So this would be an example what we could have if we have a 5-dimensional vector space. This is just an example, but you already see that the order how we put the vectors into the basis is important. And as a reminder from the last video, we could visualize our levels again, where the top one is the kernel of L to the power 3. And there it's really important that the vectors don't come from the lower level, so we have to exclude the kernel of L to the power 2. Which means the next level has kernel L to the power 2 without the kernel of L to the power 1. And finally, on the bottom layer, we have all the eigenvectors, so we only have to exclude the 0 vector. So these are our 3 levels where we can put in our 2 chains. So the first one goes from x13 to x12 and then finally to x11. So we actually go from top to bottom, but in the basis we have to go from bottom to top. And in a similar way, our second chain now starts on the second level. It could also start at the third level or at the first level, but in our example it starts at the middle level. Okay, so this is just a visualization for the Jordan chains, but now we can say what it actually means in formulas. Indeed, we already know that the chains are connected by applying the linear map L. This means L of x13 is equal to the lower level x12. And this just repeats until we reach the first level given as x11. And there we know this has to be an eigenvector corresponding to our chosen eigenvalue 0. This makes the formula simpler because we can just say L applied to x11 is equal to the 0 vector. Okay, and now these 3 formulas completely explain our first Jordan chain. And now the second one works similarly, but you know it's shorter, there we start at the second level. And that's it. This is how we want to choose our basis, in that order and with this condition for the vectors. And now the claim is that our matrix representation is given by a Jordan normal form. In fact, this is quite easy to check because we only have a 5 times 5 matrix here. And you know we get the columns of the matrix if we apply the canonical unit vectors to it. And now we can just use the picture from above, which means we write the matrix representation as a composition. This means the first thing we have here is L of x11. So what we get out in this case is just the whole 0 column. And now we can just do the next calculation for the second column as well, which means we put in E2. This means now we have to look what L of x12 is and we already know it's x11. But x11 is the first vector in our basis, so we get e1. And there you should already recognize that this works for all the other equations as well, so we shift the index here for e2 to e1. So similarly from e3 we go down to e2. But now please note, for e4 it's different, because there we jump to the second chain. Hence there we have L of x to 1, which is an eigenvector, so we get out the 0 vector here as well. So you see, we always have this 0 at the start of the chain. But then inside the chain it continues, so e5 is shifted to e4 again. And with that we are done, because we have all the columns of our matrix representation. So I would say, let's explicitly write this matrix here on the right hand side. It's a 5 times 5 matrix, but most of the entries are 0. Indeed, the first column is completely 0, but the second one has a 1 on the top. And then the third column has the 1 on the second position. And there I should recognize that this 3 times 3 matrix is a Jordan box and exactly given by our first Jordan chain. Okay, and then the next column is completely 0 again, and the last column has a 1 at the fourth position. So we find a 2 times 2 box, which corresponds to our Jordan chain. So we know that the size of the box has to be equal to the length of the chain. Moreover, you should also see that we have the 1s above the diagonal because of these connecting equations. This is the reason why we have to choose the basis in this way to get out this special form for the Jordan boxes. Okay, now with that general explanation out of the way, let's look at an explicit example for a matrix. And maybe to make it interesting, let's choose an 8 times 8 matrix. But it should not be too complicated, so most of the entries are zeros again. So this one here is the whole matrix, and as always, to transform it into the Jordan normal form, we first have to know all the eigenvalues. Which means we have to calculate the characteristic polynomial. It's some work for an 8 times 8 matrix, therefore I only show you the solution here. In fact, it's 2 minus lambda to the power 8, which means 2 is the only eigenvalue of A. And that implies for the rest of the calculations, we can just consider the matrix n given as A minus 2 times the identity matrix. So we have to calculate the powers of n and look at the corresponding kernels. And there I would say, let's do it really quickly. So let's immediately calculate n to the power 2. There, not so surprising, we get a lot of zeros again, and indeed only the first and the last row are non-zero rows. And now multiplying that with n again, we see that we don't have any non-zero entries anymore. So n cubed is already the whole zero matrix, which results into the largest kernel we have. In other words, 3 is our fitting index, and we also know all the dimensions of the kernels. The easiest one to see is the kernel of n cubed, because the dimension is simply given by 8. It's the maximal possible, and we know it has to be equal to the algebraic multiplicity of our eigenvalue. The next one you can also read from the matrix, because the two rows here are actually the same, so we have a dimension of 7. And then finally for the last one, you have to consider the original matrix n, which we didn't write down, but you can believe me that the kernel is 4-dimensional. Indeed, this is not hard to check at all, you just have to write down the matrix and you see it. Obviously the calculation is not the important part, the key element is that you can use this information here to write down the Jordan chains. So as before, we can see that we have exactly 3 levels. On the third level we have the dimension 8, then on the second level dimension 7, and on the lowest level we have the eigenspace dimension of 4. However, to fill in the picture correctly, we need to know the jumps from one level to the lower one. Indeed, the size of the jump tells us how many vectors we have in the given level. We go from 1 to 7, which is 1, and we go from 7 to 4, which is given by 3. And to make the picture complete, we also can write down the last jump, which always goes to 0, so we have a jump of 4. Therefore, we now also know the number of dots we can put into each level, so let's do that. Here we have 3, and on the lowest level we have 4. These are the generalized eigenvectors, and we know we can connect them to Jordan chains. So the Jordan chains are fixed. We have one of length 3, two of length 2, and a single one of length 1. So 4 Jordan chains correspond to 4 Jordan boxes. They fill in the whole Jordan block, which is already the whole Jordan normal form in this case. So maybe let's do that together. Let's construct the 4 Jordan boxes. The first one has size 3, so we find it as a 3 times 3 matrix inside our 8 times 8 matrix. Then we have 2 smaller ones of size 2, so we have 2 2 times 2 matrices. And finally 1 times 1 matrix. And since the eigenvalue of the original matrix A was 2, we put 2 on the diagonal. And then finally, to make the Jordan boxes, we have to put 1s inside each box above the diagonal. So we have 2 1s here, 1 here and there, and in the last box there does not fit a 1 anymore. And that's it. This is the Jordan normal form of our matrix A, and you immediately see we can write it down in the moment we know all the dimensions of the generalized eigenspaces. Because then we know the jumps and all the Jordan chains. Of course, you could say you have the freedom to change the order of the chains, which would mean that the boxes also change the order inside the matrix. However, this is the only thing you can do, otherwise the Jordan normal form of A is fixed. Okay, I think that's good enough for this example. If you want to see more examples, I have a whole video series about this Jordan normal form. The next thing we will do here is to use the Jordan normal form for a matrix to prove some general results. In fact, now we have shown that every complex valued square matrix is similar to a Jordan normal form. And how we can use that, I show you in the next video. So I hope we meet there again and have a nice day. Bye bye.